Math 265A, Quest to College. I'm Joe Vasta, and in this video we are going to cover section 3.8, Implicit Differentiation. So what is the deal with implicit differentiation? What does it mean? We're going to find that out. So we'll start by doing a problem. Find the slope of this graph at the point 2, 3. So that is what we're going to do. Now, how would we do this? Well, the only way we know how to find the slope of a graph is finding the slope of a function. Is this equation a function? Does it represent a function? The answer is, well, let's just try to solve for y and see if we can get something that looks like a function. So that's what we're going to do first. Solve for y. Okay, so I have y cubed equals 6x squared plus 3. I just added 6x squared to both sides. And then I'm going to take the cube root on both sides. So y equals the cube root of 6x squared plus 3. Okay, now when you take the cube root on both sides, you do not have the plus or minus. That only happens when you take the square root or any even root. So the cube root, we have this right here. So we can solve for y, and this is a function. It's just kind of written in a funny way. And we're trying to find the slope of the tangent line at this point here. Now it doesn't say tangent line, but it's implied in here. So let's go ahead and find the slope function by taking the derivative. Before I take the derivative, I want to write this cube root as a 1/3 power. So we have 6x squared plus 3 to the 1/3 power. Okay, so now it's time to take the derivative. And we're going to use a little chain rule here. We have something to the 1/3 power, so the derivative of something to the 1/3 power is 1/3 times that something. And then we replace this with 1/3 minus 1, which is -2/3. And so now we've taken care of the 1/3. We can ignore it now. And the derivative of the something, the derivative of the inside, happens to be 12x plus 0. So this is just 12x. Okay, so a few things are going to happen to simplify this. The 12 and the 3, they reduce to 4/1. And then we have this right here has a negative exponent, so it's good practice, in this class at least, to express your answers with positive exponents. So I have a 4x on the top of the fraction. And on the bottom we have 6x squared plus 3 raised to the, cross the line, change the sign, raised to the 2/3 power. This is my slope function, and this will tell me the slope at any point on this function. Okay, so let's go ahead and find the slope at the point 2, 3. So what number are we going to stick into that slope function? Well, we're going to stick the 2 in there because there's x's there. And one of the ways I've been doing this is I've been using this notation where we go y prime and then we put 2 in there, because it really is a function of x. So let's see what we get. We get 4 times 2 This is all over. 6, and then 2, this is 2 squared, which is 4, plus 3 to the 2/3 power. Okay, so looks like I have 8 on top, and on the bottom I have 24 plus 3. I'll just write that 27 to the 2/3 power. 8 on top. We take the cube root of 27. Okay, so the power's on the top, the root's on the bottom. Remember that roots grow underground. Cube root of 27 is 3. 3 squared is 9. So when they ask us to find the slope of this equation at the point 2, 3, we found it. It is 8/9. So I'm going to say 8/9 is the answer. So we have not done implicit differentiation, we just did a regular problem. Before I go ahead and show you another way of looking at this, I'm going to find the tangent line, and I'll do that in purple. So find the tangent line. At 2, 3. Well, look at this. I have a slope of 8/9, and I have a point 2, 3. And for all you paranoid people, you know, who have trust issues, maybe right at the beginning, you probably wanted to see if this point was on here. Now, the problems in the book should be legitimate. They're not going to say, hey, find the slope of this, and then give you a point that is not on there. Now watch this point not be on there. Hopefully that doesn't happen. So I stick 3 in for y. I end up getting 27 minus 6 times 4. So 27 minus 24 equals 3. So this point really is on this graph. Okay. Not that we have to check it. Also know that before I, continue, that things could have worked out a lot uglier. So I picked one that was nice because this is a tie-in to implicit differentiation. And what's the point of doing a problem that has nasty numbers for the slope for our first problem? So if this thing was not a perfect cube, like if it was 20 or something, then this would have looked pretty ugly. And I wanted something nice for our first problem. Okay, but in the real world, all different kinds of things happen when you're finding the slope. Now, having said that, I have a point and a slope, and I have this y equals mx plus b. 4 letters, 2 of them are variables and 2 of them are constants, and we know one of the constants, 8/9. So y equals 8/9 x plus b. So we put that in there. Now I'm just going to put this point in there, figure out what the line is. So I have 3, that's the y value, equals 8/9 times 2 plus b. So we'll bring it up here. 3 equals 16/9 plus b. Sometimes I'll multiply the equation by a 9, clear the fraction, and other times I'll just say, hey, I'm tough. Let's go ahead and do subtraction. So I'm going to subtract the 16/9 on both sides. And this is really, if you got a common denominator, this is really 27/9. 27/9 minus 16/9. So what's 27 minus 16? I believe it's 11. So we found our other constant, which is 11/9. I have just enough room to write the tangent line. Y equals 8/9 ninths x plus 11 over 9. We'll see pictures of this, but if you wanted to actually graph this on a computer algebra system, or maybe you would graph this one right here, and then you can graph the point 2, 3, and then graph this tangent line. I'll show you what that looks like after. But the main drive is to kind of ease into this implicit differentiation. So there is another way of doing this problem. You know, like this was bad in the sense that we had to solve for y. But it happened to be a function. Okay, so that was cool. We were able to solve for y. There's going to be some equations that have x's and y's in them where you cannot solve for y. You can't solve for y and give an explicit formula. You kind of have an implicit thing going on, and that's where we have this word implicit. So we're going to go ahead and do this problem again. So I need a piece of paper to do that. We're going to find the slope. We already know the answer, but this is going to ease us into the technique of implicit differentiation. So let's go ahead. I'll just keep this here for now. And there is another way. You won't be able to do all these kinds of problems two ways. Sometimes you will not be able to do the first way. So another way is called implicit. It's right up there, but I'm going to write it again. Implicit differentiation. Okay. And so let's go ahead and rewrite this equation. And I'm going to do something on purpose here. So I'm going to write this equation, the y cubed minus 6x squared. I'm going to space it out a little. And then put the 3 like right there. Okay, so I space things out. And then we also have the point 2, 3. Okay. So let's get rid of this piece of paper and take a look at implicit differentiation. So what does implicit differentiation say? It says I can hit both sides of this equation with derivative. Okay, so remember when you took pre-calculus, or maybe it was intermediate algebra, whatever it was, you found there was a new operation you can do to both sides of the equation, and that was taking the log of both sides. Okay? And you know, you saw that and you went, wow, that's kind of cool, and that was a new thing you could do. Well, now you can hit both sides of an equation with the derivative gun. So that's what I'm going to do. D dx of the left-hand side equals d dx, and I'll put parentheses around there even though I don't need that for that one, d dx of the right-hand side. Okay, so that is what we can do. Now here's the deal. We're taking the derivative of y cubed with respect to x. So this is a tricky thing now. We've never done this before, and we will get a lot of practice on this kind of deal on the next page. But for now, let's go ahead and take the derivative. Now, look at this. This is y cubed. To take the derivative of, okay, let me just, I think I should do an extra step. D dx y cubed. And then we have, I'll go minus d dx 6x squared. I think we can do that one. And then this is going to be, I'll just write this up again. D dx of 3. So here's the tricky part. To take the derivative, I am actually doing the chain rule here of y cubed. Okay, I have to take care of like something cubed. Something cubed, the derivative of that is 3 something squared. So now I could actually, remember when we first did the chain rule and then I said, okay, so we can cross out that 3 now. Now I'm taking the derivative of y with respect to x. So wouldn't that just be dy dx, or that would just be y prime? Now you can't put these together. You can't write this as, that is not a 1, that's a prime, okay? So you can't write this as y to the third or whatever. You have to keep those separate. These are actually different variables. Y prime is different than a y. And when I first saw this, that drove me crazy. Okay, let's take the derivative of this. So we have minus 12x. If this felt weird here, we're going to practice more of these things on the next problem, or maybe after a few problems. Okay, what does this equal? On the right-hand side, the derivative of a constant is 0. What I'm going to do, I'll put a box around this. It's y prime. I'm going to solve for y prime. To solve for y prime, I'll add a 12x to both sides. So I have 3y squared. I'll keep this boxed so you won't have the temptation of trying to put it together with the y squared. This equals 12x. And then I'm going to divide by 3y squared. So y prime equals 12x over 3y squared. Let me just write it one more time. Y prime, and I won't put a box around that now, equals, we can reduce this, so it says 4x over y squared. Now this is the same y prime that we see right here. So you see the 4x on the top, and then we have a y squared. You can solve for y and put it in there, but I'm not going to do that. So I'm just saying that the derivative, the slope function, now is a function of 2 letters, which is a new thing. I mean, we don't know what 2 variable functions are, but that's kind of what they are. And so now they want the slope at that point. So I'm going to go y prime, and I want to evaluate it at the point 2, 3. I'm going to use this notation that some of you might feel uncomfortable with. Put a line down there, and then put the point that I'm evaluating it at, 2, 3. So what does that mean? I put 2 in for x and 3 in for y. So 4 times 2 all over 3 squared. So what does this give me? This gives me 8 over 9. And 8 over 9 is what we got when we did it the first time. Okay. And we found the tangent line at the point as well, so that's what it was. And this is implicit differentiation. We are hitting both sides with the derivative gun with respect to x, and when there's a y, this crazy thing happened where we did the chain rule. We said 3y squared, and then it was just a y, and the derivative of y with respect to x is dy dx, which is a y prime. But before we move on to some drill and kill problems, I want to do a few more things with what we just did here. Okay, so on the next page, I'll have our original equation, and then also this thing right here. Okay. So there it is. There was our original equation. And then here's the derivative written in terms of x and y. So this question says, find the point or points where the graph has a vertical tangent. So they'll ask these questions in your homework. So vertical tangent is a tangent that looks like that. Okay, and you know, before we used to say, oh, we don't like that, you know, but now we're going to start getting graphs that this one is a function, but we're going to get ones that may not be functions. And then we talked about differentiability at a point and vertical tangents, but let's just do this anyway. It would have a vertical tangent if, here's the slope function, if the bottom was 0. Okay, so let's go ahead and see what we get for this, okay? So the bottom of the slope is 0. So I'm going to set y squared equal to 0. So what does that tell me about y? Y equals 0. Okay, so this thing will have a vertical tangent line. And once again, some of you are feeling uncomfortable with that, but it's going to have a vertical tangent line for any point where the y is 0. So they're asking us to find the point, or the points. We're going to put 0 into the original equation to see what the x value is. Okay, so let me use some arrows here. We set the bottom equal to 0. Then we're going to put that in there. Tell me these arrows aren't confusing. Okay, so I have 0 cubed minus 6x squared equals 3. So 0 cubed is 0, so I have negative 6x squared equals 3. X squared equals, I'm going to divide both sides by negative 6, so this is negative 1/2. And when I do the square root property, this does give me plus or minus. But look what's under that square root. A negative number. Negative number under a square root is still a number, but it's not a real number. So this is an imaginary number. And when you're looking at the graph of this, you're looking at real numbers on the x-axis and real numbers on the y-axis. So there's no way we can find any points where the graph has a vertical tangent. So the answer is, find the points where the graph has a vertical tangent. The answer is none. Don't you hate when you do a lot of work all for nothing? Okay, well actually this is something. This gives us information. It says the graph doesn't have a vertical tangent. Now, find the point or points where the graph has a horizontal tangent. Well, where the graph will have a horizontal tangent, that's where the slope, okay, we're looking at the slope, that's where the numerator is 0. That's when the slope is 0. And so that would, you would then set for x equal to 0. And should I do it? Yeah, why not? So we're going to have a lot more arrows. Set that equal to 0. So what does x equal? X equals 0. Then what do you have to do with that? If you're trying to find the points, you're going to plug that into the original graph. So what am I going to get? I'm going to get y cubed minus 6 times 0 squared equals 3. This is y cubed equals 3, which I'm going to take the cube root on both sides. So I will not have a plus or minus this time. This is going to be y equals the cube root of 3. So find the point or points where the graph has a horizontal tangent, 0, comma, the cube root of 3. Okay, so what I did is I graphed this on a computer graphing program. And that's what the graph looked like. It is a function. And you can see, like if you're drawing tangent lines to like at a point on the graph, you cannot find a point on this graph where you would draw a vertical tangent line. Okay, and that's why we got none for problem 2. Now, is there a place on this graph where you can draw a horizontal tangent line? Yeah, at this point right here. And my guess is that point, it's between 1 and 2, that would be the cube root of 3. Let's take a look at this a little more close. There's the graph again. Here's the point 0, comma, the cube root of 3. And look, there's the tangent line. It's nice horizontal. The first problem we did, we had the point 2, 3. We actually, I think it was in purple, found the tangent line, and it was like y equals 8/9 x plus 11/9. And I graphed that, and it went right through it. So yeah, all the stuff that we've been doing in calculus, where we're finding tangent lines and looking at slopes, that's what we're doing here. The new thing for section 3.8 is the implicit differentiation, which we hardly did that much of. So now we're going to work on that skill, and we'll see some more graphs. And the graphs, here's the deal. They're not always going to be functions like this problem. So the graphs may look crazy. They could be circles, they could be loops, they could be lots of different things. And now with implicit differentiation, we can analyze slopes of things that are not functions. And you'll see that as we continue. Okay. Oh no, I just hit the tripod with my hand. So I got to put the other piece of paper on, and then I also have to make sure that we're still in range. Okay, that's going to be good enough. So now what we want to do is we want to take some derivatives. Here are 5 kinds of problems that you will not see in your homework. These problems are just going to help us have more confidence when we see the harder problems. So problem number 1 is something that we already should know how to do before even hitting this section. There's the derivative gun. You're supposed to take the derivative with respect to x of x to the 4th. So we know that this is 4x cubed. Okay, now I'm going to tell you something that's going to upset you. When we've been taking derivatives of just stuff like this, polynomials, we were actually doing the chain rule. And some of you are like, say that isn't so. Well, we were. Vader betrayed and killed your father. I mean, so we've always been told things, and then later on we're like, oh yeah, so it wasn't a real lie. I never lied to you, but look, something to the 4th, the derivative of something to the 4th is 4 something to the 3rd. And now the derivative of x, that's dxx, or dx dx. What do you think dx dx is? That's just a 1. So let me go ahead and write that out. This is just a 1. How do you, okay, that's supposed to be a 1. Okay, that's just a 1. So we never did that. There was no need to tell you, oh yeah, by the way, we're doing a chain rule here, because when we first learned this, we didn't know the chain rule. But now I'm just saying that, hey, when you have an x, you're really going dx dx after you've finished up doing your little shortcut. So the answer right here is 4x cubed. The reason I do this is because it makes a good comparison to this right here. Okay, so now I'm taking the derivative with respect to x of y to the 4th. And so we kind of did something like this on that first problem, it was like y cubed. So this is really something to the fourth. The derivative of something to the fourth is 4 something to the third. And guess what? The chain rule says, okay, we're done with that 4. Now you're just taking the derivative of y. You're going d dx of y. And if you kind of put the y up top, it's going to say dy dx. And this is an acceptable answer here, by the way. But I'm going to go ahead and write this as 4y cubed y prime. And so both of these happen to be the chain rule. Chain rule. Chain rule. Even though lots of times, you know, a lot of teachers will say, well, you're not really doing the chain rule here. You're not, but in spirit you are. Let's go ahead and do a few more problems here. The derivative of e to the 2x. Okay, so this is the derivative of something. Of course it's the derivative of something. This is the derivative of e to the something. The derivative of e to the something is e to the something. Okay, so now I am doing the chain rule here. Okay, the e's gone. Now let's go ahead and take the derivative of the something, 2x. What's the derivative of 2x? It is just 2. We're really taking the derivative of 2 times something. And after we do that, and this might confuse you and you might not want to write this down, what you're really doing is then at the end you're going dx. dx, just like we did up there. I'm not even going to attempt to draw a big number 1. That's what that was supposed to be, by the way. I was trying to draw a big, bold 1. This is just a 1. And so I would say in the future, if you're just taking the derivative of things with just x's in them and you're going d dx, not to write that, but I'm writing that so it helps you with problems 2 and problems 4 and 5. So our final answer then is 2e to the 2x. And the dx over dx is just 1. Of course, that's the chain rule as well, but I'm not going to point an arrow to that. Okay, so now, here's this one. The derivative of e to something is e to something. Okay? Chain rule. Now, we've just jumped over the fence, and now we're out to kill the dog or whatever. If you didn't see the last video, then you're probably like, what did he just say? What's the derivative of 2 times a variable? It would just be 2. Okay, so now we're done with the 2 there. And now we're just taking the derivative of y with respect to x, which is dy dx. Which, whenever I see this, I'm going to replace it with a y prime because that's less writing. So let's clean up this answer. We'll put the 2 in front. 2e to the 2y power times y prime. And in fact, I guess it's a good rule of thumb that whenever you're taking the derivative with respect to x of something that has a y, you just do this normally. You pretend like that's an x, and then that's what the answer is, and then at the very end you multiply it by a y prime. So that's how I'm going to play the game. You take in the derivative with respect to x of something with an x, just do it normally. But if it has a y in it, then do it normally and then put a y prime. Put a little marker next to it to show that, oh yeah, this was a y. That's going to help us on this problem, because on this problem what we have is we have the product rule. We have this times that. Okay, so I'm going to do the product rule, and anytime I zap something with the d dx derivative gun that has a y in it, I'll put a little marker next to it, okay? So, the derivative of the first, that is 3x squared. I'm not going to go ahead and go dx dx, okay, because I'm over that now. In fact, I'm really embarrassed on how, maybe I can fix that. Usually when you go to try to fix something, it makes it look worse. Is this going to, oh gosh. Well, maybe the one's like pointed at the top. that looks, I still don't like it. Oh well. Okay, the derivative of the first times the second. Now you might be thinking to yourself, don't you put a y prime next to it? Did I ever take the derivative of the second? At this point, no. I said derivative of the first times the second plus the first times the derivative of the second. So now I'm taking the derivative of something that has a y in it, and I'm using the chain rule, so I'm just going to say, well, if this was an x and it said x to the fifth, what would I do? I would say 5x to the fourth, but I'm going to put 5y to the fourth, and then because I took the derivative of something that had a y in it, this is with respect to x, I'm going to put a y prime. So look what we have here. I'm just going to clean it up and not write the parentheses, put coefficients in front. 3x squared, y to the fifth, and then this is going to be plus 5x cubed, y to the fourth, and then y prime. And there's the answer. Kind of wish the book had problems like this, but the deal is, if you've made it through these problems, you're ready to do the tougher problems that we're about to do. And it will have these skills in it. Okay, so this is implicit differentiation. Let's take a look at we'll start renumbering our problems at 1. Find the tangent line to y cubed plus x squared y plus x squared minus 3y squared equals 0. At the point 1, 1. Now, what I'm going to do this time is I'm actually going to show you the graph of this. You can graph this on a computer algebra system. You might think to yourself, well, can I solve for y? No, you can't solve for y. There may be a way where you can solve for y and kind of have 3 representations. I'm not saying it's impossible to solve for y. A cubic equation, because that's what that is, has 3 solutions. It's like a quadratic equation has 2 solutions, except the cubic equation is more complicated to solve. And what you end up, if you just graph this, so you end up getting this. Look at that. Does that look fun? Woo! Yeah! Okay, looks like a roller coaster or something. If you were to solve for y, you could actually try to find some equations that define 3 functions. The orange part is a function, isn't it? The green part's another function, and the blue part is another function. And now this is something that is in higher math classes, and not all math majors will study this kind of algebra, so that they go into different fields. So this is just something that we wouldn't want to figure out those 3 functions. What we want to do is there is the point 1, 1, which is right there. We want to find the slope at that point, and not just the slope, the tangent line. So what is the tangent line at that point? That's what we're going to do. Okay. Oh, I made the tangent point too. I really pressed into the piece of paper, and it like got so dark it went through there. Yeah, now nobody even knows that happened, except it's on video. Okay, so what I'm going to do is I'm going to write out this equation. This equals 0. So I'm going to hit both sides of this equation with the derivative gun. D dx over here is dx. Now after a while, you might decide, oh, I don't need to write that step. I know what I'm doing, and then you just attack this with the derivative gun. But I'm going to do it this way. Okay, the derivative of y cubed. Well, it's 3y squared. But don't forget to put the little marker, which is that right there. Now because I am doing a whole equation with this and I'm going to be solving for the y primes, this is just a personal preference, you don't have to do this. I'm going to box my y primes because I find that when I don't, sometimes I lose them. It's a bad thing. You don't want those to absorb each other, but sometimes I do that, so that's why I box them. Okay, we've done the derivative of this. Now we're going to do the derivative of x squared y, which happens to be a product rule. Okay, so I'm going to say the derivative of the first times the second. So no y primes yet, plus the first times the derivative of the second. Well, what is the derivative of y? It would just be 1, and then you've got to put your little marker, which is y prime. Okay, so that takes care of that one right there, the x squared y. Okay, plus the derivative of x squared. This is all with respect to x, so this is just normal. 2x. And then right over here is the derivative of negative 3y squared. That's going to be negative 6y. So you just pretend like that's an x when you first get going. And then because it was a y, you put a y prime. That's the left-hand side. And the right-hand side, well, this one's pretty intense. What is the derivative of 0? Well, it's just 0. Okay, so what I'm going to do now is sort of just clean it up a little. So 3y squared y prime. Maybe it doesn't need cleaning up. And then this is plus 2xy. And then this is plus x squared y prime plus 2x minus 6y y prime equals 0. Okay, so I have 5 terms on the left-hand side. I'm trying to find a tangent line. Okay, that's what I'm trying to do, but I'm trying to find a slope expression, which is really y prime. So I want to have y primes on one side of the equation and the other non-y primes on the other side. So I'm going to put, this is a non-y prime. This doesn't have a y prime, that's what I'm trying to say. And this doesn't have a y prime. So I'm going to put those on the other side of the equation by subtracting. So when I do that, I end up, let me just circle them. Red Rover, send 2xy right over. That actually is a cruel game. Red Rover. Who thought of that? I mean, for one thing, they're making kids hold hands with other kids. And when I played that game, I always had to stand next to the kid who always had to wipe his nose and wouldn't let go of my hand. That sucked. The other bad thing about Red Rover, you know, people talk about dodgeball. Oh, that's cruel. At least you have a chance, okay? It could be cruel, but Red Rover, send the big kid right over, and then the big kid comes. There is no way I'm going to continue to hold hands when I have a big kid coming over to try to break through. I'll just let go and let him slam into the wall. But I mean, it is a cruel game. So, wow. Okay, that was quite a tangent. Okay, so negative 2xy minus 2x. We did send those guys right over, didn't we? And then we have 3 terms here. Those 3 terms each have a y prime. So with the 3 terms that I have left over here, I'm going to factor out the y prime. Some could argue you shouldn't have done that all in the same step, Joe. I'm going to go ahead and email the dean of the college to tell the dean what you just did. You skipped some steps. Okay, so factoring that out, factor a y prime out, I have a 3y squared, and then I have a plus x squared, and then I have a minus 6y. And then go like that. Space things out so it looks like I planned it that way. And so I have a slope expression that looks like this. It looks like negative 2xy minus 2x all over 3y squared plus x squared minus 6y. Now the bottom is not going to factor. I mean, if this was a negative 6xy, it might be able to be factored, but it's not going to factor. So factoring out a negative 2x on the top, I mean, that's cool, but it's not going to help simplify this fraction. This fraction is what it is. And it almost feels at this point, for many reasons. One reason is we're kind of out of paper. Another reason, it just seems like, okay, it just seems like we're done with this problem. But remember what the problem is asking us to do. It is asking us to find the tangent line at this point 1, 1. Now, we have a point 1, 1. We'd like to stick that into the slope function. So the notation to do that, and I think we've already seen the notation to do that, so I'm going to take part of that problem off, go to the next paper, is to go like this. We're going to go y prime evaluated at the point 1, 1. So when I do that, we should be able to find the answer. So what do we have here? This is pretty simple to do because they're both 1s. I mean, if one was a 1 and one was a 2, you'd have to be careful where you're plugging those numbers in. So the top's going to be negative 2 minus 2. The bottom is going to be 3 plus 1 minus 6. Okay, so we have negative 4 on the top, and on the bottom you have negative 2. So negative 4 over negative 2 is a positive 2. There's your slope. Now the point, of course, was the one they gave us, which was 1, 1, and the directions are to find the tangent line at this point. So let's go ahead and do that, writing down the y equals mx plus b. Move this up like this. We know one of the two constants. The constants being m and b, we know m is 2 for this problem. And we have to figure out what b is by plugging that point in there. Well, x is 1, y is 1. So 1 equals 2 plus b. What does b equal? Well, b equals negative 1. So our final answer for this, because we are trying to find the tangent line, is this right here, which is y equals 2x minus 1. And this is all thanks to implicit differentiation. 2x minus 1. So here was the graph. This almost seemed impossible. Hey, find the slope, find the equation of the tangent line there. And you had this? Before implicit differentiation, there was just no way we can do that. Now we can, and it is 2x minus 1. One thing that we never did see was, you know, like I said, if you were paranoid, to see if 1, 1 actually does satisfy that equation. And it does, because look, 1 plus 1 plus 1 minus 3. So that's like 3 minus 3 is 0. So this point is on there, and you can see on the graph. So the visual satisfaction is this right here. So I went ahead and plotted that point on the computer software. There is 2x minus 1. It does have a slope 2 and a y-intercept of -1, and it just kisses the graph right there. So implicit differentiation, woo! Way to go. Let's go ahead and do another problem. Problem number 2. Find dy dx. So we're not going to do the tangent line or anything like that. We're just at a point. We're just going to go ahead and see if we can do implicit differentiation. So if you want it to be a little lazier than the last problem, you can just go like this. I'm going to apply d dx to both sides of the equation. Okay, the first term here is a product. Y times e to the 2x. So let's do the product rule. The derivative of the first, which is 1, oh, it's a y, so I'm going to put a y prime. The derivative of the first times the second. You don't need those big parentheses, but I'm doing that because this is an online setting and people can't ask questions, so I figure when I do this, some of you are like, oh yeah, he's doing the product rule. Derivative of the first times the second plus the first times the derivative of the second. Now the derivative of e to the 2x is a little chain rule, so e to something is e to something. And then the derivative of 2x is just 2. And notice I threw the 2 in front when I did that. So that takes care of the derivative of that term there. Now we're going to take the derivative of sine 3y. The derivative of sine of something is the cosine of that something. Okay, so I'm doing a chain rule here. So that gets rid of the sine. Now I'm taking the derivative of 3y. What's the derivative of 3y? Well, it is 3. That takes care of the 3, and now because I took the derivative of something with a y in it, I'm going to put a little marker, y prime. So now I've got 2 little markers so far, a y prime here and a y prime there. Here a y prime, there a y prime, everywhere. Never mind. Okay, now I'm taking the derivative with respect to 6, which is 0. And then the derivative, did I say with respect to 6? The derivative of 6 with respect to x, and the derivative of this guy with respect to x. This is 6x squared. Okay, they asked me to find dy dx. Now dy dx is the same as y prime. So, I mean, both are the same. Well, we're going to go ahead and clean this up a little. So I have e to the 2x y prime. That's just a matter of style that I went ahead and put the y prime on the right side. You can keep it the other way. This is going to be plus 2e to the 2x y. And we have over here, we have plus, I'm going to throw both of those guys in front of the cosine 3y. So this is 3y prime cosine 3y. Let me just emphasize again that it's just a matter of style, me putting boxes around those y primes. It's so I don't lose them. This equals 6x squared. Okay, so it looks like I want to get my y primes on one side of the equation, and they are on one side of the equation, and the things that do not have y primes, I'm going to put them on the right hand side. So I'm going to go ahead and take that guy over to the other side. And So when I do that, it ends up giving me 6x squared minus 2e to the 2x y. That's on the right-hand side. And on the left-hand side, I'm going to do what I did in the last problem. I just see two terms now. I'm ignoring the orange thing because it's over here. I'm going to factor out the y prime. And so I have e to the 2x plus 3 cosine 3y. Okay, and then there's a little space there. I don't know what happened. And now what I'm going to do is I'm going to divide both sides out by this part right here, the e to the 2x plus 3 cosine 3y. So divide both sides by that, and I'll have an expression for y prime. So y prime equals this fraction here, 6x squared minus 2e to the 2xy. And then on the bottom I have e to the 2x plus 3 cosine 3y. And that's all they wanted me to find. I mean, you can call it dy dx or you can call it y prime. There it is. This gives you the slope at any point that's on this graph. Now the thing to remember about this graph right here is you can't just pick any x and y value. You can't just say, oh, well, let's just say x is 0, y is 0. It has to, that point has to be on this graph, and then this gives you the slope of that point on the graph. Okay, so these are x and y values or points that they should be on here. Now the thing that I'm going to show you, even though we don't need to do this, I just think it's really interesting. You cannot solve for y on this one. Okay? There's no way, because there's a y in the argument of the sign, and then there's a y there. When you go to plot this graph on a computer, it is not going to be a function. It does not pass the vertical line test. And yes, the other one, the roller coaster one, I didn't say vertical line test, but it didn't pass it. It wasn't a function. I assumed that we knew that. So here is what the graph looks like. Wow. So we get some wiggling happening. Obviously, it's not a function. It doesn't pass the vertical line test. Why is the wiggling happening? Well, it's because of the sign. And then you have an e to the 2x, which you can kind of see. I mean, you see different things happening, but it's just a really weird graph. And yes, it wiggles and then like kind of wiggles down, but then it's disconnected, and there's like I mean, that's not an ellipse. It might remind you of one, and then they're getting smaller and smaller, and then it just goes into a dot. And that is just so cool. So if you had any point that was on the graph, you can find the slope and even the tangent line at that point. Now, what good is that? Well, we're not going to get into applications here, but we know velocity is an application of the derivative, but any rate of change. And there are times and places in higher math where you have to consider the derivative graph or the slope, what we're doing here, the y prime of something that is not a function. Okay, we're going to do our last problem, and perhaps you might be able to do this one on your own. It is a little challenging because what are they asking us to do? They're asking us to find this. Now, what is this? d2y dx2? So just as a reminder, and some of you can skip past this, this is taking two derivative guns and you're taking the derivative of y. So you take it, you hit it one time, and then you hit it another time. So really what it is, it's the second derivative. It's y double prime. That's what that means. And the reason for this, I'll go through this again, is people got lazy, and y, you know, even though he's in the middle, he's on the top. So this is d y over dx 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 squared. and then it was d2y, because there's two d's there. And then what happened over time, people got lazy and didn't want to write the parentheses, so they just said dx and then 2, and that's how that notation is. I hated it the first, it was at least a year when I started taking calculus, and I did not get that, and I wish someone had explained, well, why is that? Oh, that's just the Leibniz notation. Shut up and let's do the next problem. And I was like, okay, that's a good explanation. Thank you. Okay, we have this, and we know what this is. This is a circle. Okay, centered at 0, 0, and has a radius not of 4 but of 2. We have to find y double prime. So before we find y double prime, we must find y prime. To find y prime, I'm going to do implicit differentiation. Take the derivative of both sides of this equation with respect to x. The derivative of x squared with respect to x is 2x. The derivative of y squared with respect to x is 2y, and then we have to put a little marker there, so y prime. The derivative of 4 is 0. So you get a few of these problems in your homework. We're not done, but what you want to do next is solve for the y prime. So I'm going to bring the 2x to the other side by subtracting. So 2y, y prime, equals negative 2x. So divide both sides by 2y, and you get y prime equals negative 2x over 2y. And that can be simplified a little more. So it looks like y prime equals negative x over y. Now, you don't need to draw this, but here's the circle here. 2, 2, negative 2, negative 2, x, y. If you find any point on the circle, randomly pick any point on the circle, like, oh, I'll pick this one right here. You stick the coordinates of that point into this expression, and it will give you the slope of the tangent line to that point. So that's pretty amazing. Implicit differentiation is powerful. We're not done. We're trying to find y double prime. So, let me just say this equals y double prime. Okay. So keep this here, like this. So how are we going to find y double prime? I mean, we've never done a problem like this. We found the second derivative, but not when the first derivative had some y's in it. Well, what we're going to do is we are going to apply the derivative gun to both sides of this equation again. So I'm not going to write that this time. I'm just going to say y double prime is. And so that's what I'm going to do. I'm going to go ahead and take the derivative of the right-hand side with respect to x. So everywhere I hit y with the derivative gun, I put a little marker, and that marker is going to be a y prime. I see a quotient, so I'm going to do the quotient rule. Okay, so here's the quotient, here's the top, here's the bottom. So the quotient rule says the derivative of the top, minus 1, times the bottom, y. And then we have minus the top, negative x, times the derivative of the bottom. The derivative of y is 1, and then put your y prime there. Don't want to lose it, so I just box it. This is all over the bottom squared. So y double prime equals negative y, and then there's two negatives there, so this is going to be plus x y prime. This is all over y squared. So some of you are like, okay, let's just box it and leave it at that. No, we can't. Because we don't want our derivative to have 3 variables. Then you might be thinking, what do you mean 3 variables on the right-hand side? Well, one variable is y, another variable is x, and the third variable is y prime, or m, or slope. So this is slope, and then this is x, and this is y. So we can get rid of this y prime. How? We know what it is up there, and we're going to plug that in right there. Okay, so this equals negative y plus x times y prime. Y prime is negative x over y. This is all over y squared. So what do we have here? We have negative y plus, not plus, negative y minus x squared over y all over y squared. I think the worst thing about calculus is algebra and trig. And so some of you are like, okay, let's just box it. It just has x's and y's in it. But what does it have in it? It has fractions within fractions, so we cannot box it. There's actually a little twist at the very end, and a lot of you are going to be like, oh man, I hate you, Joe, but don't hate me, hate the math, okay? You shouldn't really hate the math, actually. Thinking about that, okay. On the top, you need a common denominator. That common denominator is a y, so let's give this guy a y, and then put 1 right up there. So what does this give us? The second derivative is negative y squared minus x squared all over y squared over 1. So now what I'm going to do, equal sign's a little high, embarrassingly high, isn't it? Wow. It's like I'm showing favoritism to the numerator. That's just wrong, and I'm like the math teacher. I still love you, denominator. Okay, so now I'm going crazy. You tend to go crazy. I mean, my job is teaching face-to-face, and then the state says, oh, you've got to not do that anymore. And so I've been doing videos for months now. I'm in a room talking to myself. There's a camera running. I'm pretending that you guys are here, but it's just a crazy guy talking to himself. That's just great. Okay. This equals. Okay, so here's what I'm thinking. When they start making movies again, they should make a really cool movie. Give it a good name, like The Annihilator. Now, annihilators are things that you'll see in differential equations. And so, make the trailer of that movie be so, it doesn't show much, but it has great music, maybe exploding noises, but they really don't want to show you the annihilator. And then when people go to the theater, all it is just some math instructor at a whiteboard for about 2 hours teaching differential equations. I think, even though that movie probably wouldn't make a lot of money, it would totally be worth the laughs. So, maybe I'll do that. I don't know how I'll get it funded or anything, but hey, I'm going to do a copy.flip. And some of you are sitting there like, I'd pay to see it. Wow. I mean, look, this is great. Copy dot flip. Okay, so it looks like we have negative, let's put the x squared first. So I have negative x squared minus y squared all over y cubed. So then some of you are like, there, we're done. It just has x's and y's. It doesn't have fractions within fractions. And so we're good to go. And the answer to that question is sometimes when you do these problems, you're not good to go. And you might be thinking, why not? Watch what I'm going to do. I'm going to move this paper down here. He's doing magic. What is he doing? I'm going to factor a -1 out of there. So watch this. This is -1, and then we have x squared plus y squared. This is the little twist at the end where some of you are just gonna, there's gonna be hate mail and all that stuff. You're gonna be like, whoa. So I factored a negative out of there, and then I'm looking at this x squared plus y squared. X squared plus y squared. Man, that sure does remind me of something. Why, it reminds me of this right here. And that x squared plus y squared equals 4. So just like we used the y prime to get rid of this, now we're using our original equation to get rid of this x squared plus y squared. This will sometimes happen at the end of these second derivative problems. So it looks like I can write this as -4 over y cubed. Yeah, that was nasty. That was a punch in the stomach. So if you're just sitting there going, oh, I'm feeling a little sick, well, you have been watching math. And did you think that was going to make you feel better? I don't think so. So we have just found the second derivative. I'll write it as y double prime, not d2y over dx squared. So y double prime is -4 over y cubed. Later in this class, we'll find the connection between the second derivative and the graph. But right now, we'll just say, well, that was enough work. And now we know a little about implicit differentiation. We are done. You guys have a good day. Do your homework, and I'll see you in the next video.